Hello and welcome back. Today we're going to be talking about the correlation coefficient, which we call R, the letter R. And what R does is it measures the strength and direction of a linear relationship between two quantitative variables. Okay, so basically you're going to get a data set of x's and y's, and you're going to make a scatter plot. And the next thing we want to do is find the R. Now, if they ask you to describe the relationship without giving you R or no means to find R, then you would use uh, the techniques that I taught you on the other video, which is describe the strength, direction, and form just by kind of eyeballing it. But bringing R in is a nice way to kind of make things concrete and use statistical values to measure strength and direction. Okay, so let's go over the properties. They're very, very important. And let's talk about the first property here, which is R is between -1 and 1. Okay, and what that basically means is that R cannot be 2.3. Okay, or another way to look at it is if you just think about a number line, -1 to 1, R falls anywhere between this one, scan on through, and stops right here. Okay? R cannot be over here. There's no R over here, and there's no over here. So just make sure you're aware of that. Okay. The sign of R gives the direction of the relationship. Okay, now remember the three things we always want to describe is the strength, the direction, and the form. Okay, so now we have a way to describe these two. And on number two, or the second one, gives us a more statistical way to describe the direction. So if R is positive, then you know the relationship is positive. If R is negative, then you know the relationship is negative. Okay? And I don't know why I spelled that wrong. Tends to happen, especially when you record a lot of these. Positive. Okay, so that's basically what the second property is saying. And I'll go over that more in the next video that kind of explains R. I'm not going to do that now because it's kind of confusing, but I'm going to do another video which is kind of optional, but it's really good to look at it so at least you get an idea of where this direction comes from. Okay, let's look at the third one. The correlation of R for X and Y is the same as the correlation of Y and X. So all that's saying is if you have an X and a Y here, okay, and you had and let's just say our R is 0.8. Okay, so does it satisfy 1? Yes, it does. 0.8 is somewhere right around here. Okay, so all that's saying is if you take your X's and make them into Y's, and you take your Y's and make them into X's, R will be the same. Okay, now let's look at this. If I have a small x, you have a small y. Now let's think about this. Now I'm going to change it around. Okay, I'm going to take this y and put it down here. I'm going to take this x and put it over here. So now let me change the color a little bit. Actually, let me make this look a whole bunch better because this is really messy. It's pretty self-explanatory, okay, but you know that's me and I've seen this stuff before, and if you haven't seen this stuff before it might not be to you. So here, these are my x's, these are my y's. Now look at this point right here. That's a small x and a small y. Now if I change the y's and the x, now let's look at this one right here. Now this is a small y, and it's a small x. Now my x's are on the y's now, so that they're both small. So you'll kind of see that work. So it's still going to be a positive relationship. The r stays the same. So like I said earlier, if r was 0.8, when the x here and the y, if I switch them around, r will also be 0.8. Okay, so that's that one. Okay, the next one, r does not have units. That's going to come in handy for the next videos, but I'll give you a quick version. Okay, r is found by summing the standardized x's with the times the standardized z's divided by n minus 1. So what happens here, z's do not have units. Z's, if you remember, are just how many standard deviations you're away. Okay, so z of x would just be x minus the average in your data set divided by the standard deviation of that data set. Okay, so we lose all we use our value, we lose our units. So if x was in feet, okay, we would lose our units. Okay, which means z does not have units. So no units times no units is no units. Divided by n is just how many are in your data set. Okay, so r does not have units. So if you ever see something where it says uh, 0.8 feet, this would be an example. R equals 0.9. I'm going to change it not from 0.8, but I'm going to say 0.9 feet. This would be a mistake. Can't have that. Okay? There's no units on that. Okay? So now let's look at the next one. R is not affected by changes in the scale of the x or y axis or changes in the units of x or y. These are all very, very, very important. And I've talked about this on an earlier video, saying that if you go from feet, let's say your x's are in feet units, and you change them to, let's say miles. Okay? And let's say your y is in time, so I'll say you're going to go from years to days. Okay? So let me clean this up a little bit. Oh, I'm so messy tonight. Probably because the Olympics are on. But I had to turn my TV off. So it makes a funny buzzing sound when the TV's on. Okay, so let's go. This is feet. I'll do it on two separate ones. And this is on years. Okay, and let's change it up a little bit. Okay, and to change it up a little more on you, it's going to make more sense because really scatter plots are just special timelines. Scatter plots mostly is time going on, what's happening. Okay, so I've noticed as the years go on, the feet are getting smaller. So r is the direction. So since this is a negative, since this years is getting bigger, the feet are dropping. I'm going to say this is an r. This looks like an r of probably about 0.87, and it will be negative. Okay, so r equals negative 0.87. Here's an example. Let's say I change the years to days. Okay, years to days. So years, this is one year, and 2 years, and I'm going to days. This would be 365, and so on. Okay, so what happens? It's getting more spread out. So these aren't going to be as compact. And I change these feet to, let's say, miles. Okay, or let's just say inches. That's a little bit closer. So what's going to happen is these are going to be more spread out. Okay, and in the inches, okay, feet, if I go to inches, there's more inches, so these would be more spread out too. So it'd be more, I hope you see the point. It won't be as compact as these. Okay, but the r doesn't change. Believe it or not, the r doesn't change. Okay, it does not matter if you change the units or you change the scale. Essentially, that's what I'm doing by changing the units. I'm just changing the scale. Instead of going from 1 to 2, I'm going 365 to whatever, how many days 2 years are. Okay, so let's go to the next page, and we're going to go with r measures the strength of a linear relationship. That's going to be important. So we're on here now. These are all done. Okay, of a linear relationship. Okay, so this is what could happen. You could get something like this. Okay, so you have to ask yourself, is there an association there? Yeah, there's an association. Yes, it's pretty good. Is it linear? No, it's not linear. Okay, now if you did the calculation, okay, by hand, which you'll never do, or if you put it in your calculator, you may get an R of, I'll say, point 0.9, which you'll see later is pretty strong. It's a strong relationship. So if you go on your way and you start describing this relationship between X and R and you start talking about how strong this relationship is, you're making a huge mistake because the relationship's not linear in the first place. Okay, so you have to make sure that your relationship is linear. It's very, very, very important. Okay, so that's that. Okay, let's go to correlation. It's very sensitive to outliers. Okay, now I didn't talk about strength. I'll probably make one about the strength and put it before this video. So then when you're watching this, you kind of have an idea of what's strong and what's not strong. Okay, so let's say our x and our y, and our x and our y's are always in context, and they have units because they're quantitative. Okay, so correlation is sensitive outliers. So let's just say you have this relationship like this. Okay, and this is good. It's linear. They're compact. You're going to get R in this case maybe somewhere around 0.96. Now what happens if I throw this person over here? Okay, now does this person fit your trend or do they mess up your trend? Well, this person up here is an outlier. Sorry, this is an outlier. And with this one little person here, this one data point up here is going to lower your R. Okay, so that one point will dramatically maybe drop it all the way down to there. Okay, whereas you could have something like this, and then you could have one person like way over here that kind of fits your trend. This will increase your R. Okay, and we'll play with a whole bunch of software packages, and you should go on the internet and just Google R, and a whole bunch of applets will pop up, or you could play with points, drag points around, play with the strength and that stuff. Okay, and I'll just do a quick thing on the R. And if you go back and watch this video, I know I'm going fast, but I know if you go back and watch it, slow it down, watch it a few times, because I know I'm going pretty fast. I'm going to change the color here a little bit and then talk about. So if you get a straight, perfectly straight scatter plot, your R will be 1. If you get it perfectly straight in the negative direction. Now when I mean perfectly straight, meaning that you could draw a line and it'll go through every single point exactly, directly over it, your R will be -1. So obviously that's the best case, but in real life, it just doesn't happen. Okay, because it's a perfect line. There's going to be some variation. That's why we have statistics. It's a great thing about statistics. So anyways, here's another one. So the more compact it is, the closer it is to 1. So this may be 0.95. Okay, and this one would be the same thing but negative. This may be -0.95. Okay, so what are the ranges? Generally what I'll do, for me, I'll say any R from -0.5 to 0.5. Okay, I'll say this is very weak. And it's all kind of, you kind of have to play around with it. And then I'll jump to somewhere like, let's say -0.75, or let's say 0.7 to -0.75. Okay, or the same thing on the other way, so it would be zero point 0.7 to 0.75, somewhere around there. These guys here would be like moderately, and I'm talking about strength here. Moderate strength. This is where it measures the strength. Okay, and then anywhere from zero point 0.8 to 1, or negative, let me put a 0 in front here, zero point 0.8 to -1, these would be considered strong. Okay, and we'll play around with these, or you go to the internet, if you're not in a class, we'll go and play with these so much, and you'll be very comfortable with R, and you'll be able to use R to describe relationships. The last thing we'll have to learn, which we will learn in the next chapter, is how can we have a definite way statistically to say that a relationship is really linear other than just looking at it. Because sometimes you could look at a relationship, sometimes you could look at something like this and it could be a little bit less discrete, and then you could say that that thing is linear, but in reality it's not. So anyways, thanks for watching. Have a nice night.